Hello and welcome to another video of Law with Vishan Basala. Today we will be learning about theoretical analysis of Linden basic cycle with pre-cooling. In a subsequent modification, Linden made use of a prior development of Joule-Thomson in their formula for expansion of air, where Tk equal to P1 minus P2 into 273 divided by T whole square, where the pressures are a few bars and T is near ambient. If the temperature decreases, the expansion increases the temperature differential. Linden took advantage of these features by placing an ammonia machine unit between the main air compressor and the primary process heat exchanger. This added unit lowered the temperature of the process air to 240 Kelvin, which is minus 33 degrees Celsius. Presently, ammonia chillers have been replaced by other more reliable refrigeration machines that are more environmental friendly. Example, as before in figure 2.4, the air was compressed to 200 bar, but the primary heat exchanger was split into two sections. Between the two sections, process air entered a refrigeration machine, lowering its temperature to 270 Kelvin, minus 33 degrees Celsius. The property values from the T's diagram for nitrogen used as the main refrigerant are the same as for the simple high pressure Linden cycle. HA equal to 207.94 kilojoule per kg. Refrigerant at 101.325 kilopascal and at 300 Kelvin. HB equal to 250.2 kilojoule per kg. Compressed refrigerant at 681.7 kilopascal and at 272.85 Kelvin, and HC equal to 61.23 kilojoule by kg, and refrigerant at 300 Kelvin and saturated liquid, and there is a formula for it, and where R is refrigerant mass flow rate. So this is it. So this is the diagram. You have a look at it. Okay, I'm going forward. So from this numeric we'll get the improvement is this. Now let's learn about theoretical analysis of the Linden high pressure dual process. Linden also took the efficiency of the cycle another step further with the use of a dual compression cycle plus pre-cooling. He employed the simple well-known fact that the compression energy varies as the log 10 of the compression ratio. The compression ratio of the original cycles was 200 to 1 and its log 10 was 200 to 50 or T, or its log 10 was 0.6021. The process cycle is figure 2.5. Okay, there is another figure here. It's like this. We'll have a look at it. Okay, this will look at properly. Involve the initial compression of a smaller quantity of process air, 20% to 25% of the total, to a pressure of 50 bar, and then recycling this quantity from 50 to a higher pressure of 200 bar. The high pressure stream passed through a 3-channel heat exchanger and expanded. Sorry for that, okay, noise. The higher pressure stream passed through a 3-channel heat exchanger. The process cycle figure 2.5 involved the initial compression of a smaller quantity of the process air, 20 to 25% of the total to a pressure of 50 bar, and then recycling this quantity from 50 to a higher pressure of 200 bar. The higher pressure stream passed through a 3-channel heat exchanger and expanded to the basic pressure of 50 bar, resulting in the liquefaction of a portion of the stream. The unliquefied portion is returned to the high pressure second compressor after passing through the heat exchanger, cooling the incoming stream. Assuming that I is the intermediate pressure stream, flow rate ratio I equal to Mi by M, and M is the total mass flow rate through the high pressure compressor. The yield is like this. So this is a figure. You can have a look by pausing the video. So yeah, look at this. From where the main air goes, this is I think the first part, and from here the heat exchanger, there are so many heat exchanger, 3 heat exchanger, and so yeah, Linden dual pressure processes like this. So I think we'll do this up to here, and next class will be theoretical analysis of Cryogenic cycle. Thank you so much for watching. See you another video. Bye. Take care.